Hello, 115 students. I'm making an extra recording for the end of Chapter 3 that was not posted sooner because it was a long week. I'll talk a little bit more about what determines the chemical formula of an ionic compound and how they're named, and a brief discussion about what acids and bases are. One thing to make sure you realize is that there are some very obvious patterns in the ions of common elements. We talked about these already in the Pogel book last week. Group 1 and 2 elements have charges that correspond to their group numbers, and so they're going to be +1, +2, and same thing with group 3A. If you have a metal there, make sure you're not worrying about the nonmetals. Group 4 doesn't really make ions, not in general, and then group 5A will be -3 ions, group 6A -2, and -1 ions for group 7A. All of these are, of course, so that you can get an electron configuration corresponding to the nearest noble gas. The transition metals, however, are variable. This is why you need to have Roman numerals to describe their charges in their names, and otherwise you have to pay attention to the information provided to know what the charge of these things will be. You don't predict them. So no Roman numerals in the name will be needed for anything that's not in, for any metal that's not in group 1, 2, or 3A. So go on from there. So when the other part of what you have to work on with naming ionic compounds is becoming familiar with polyatomic ions. They simply need to become familiar by use, or you make a note of them on a note card so they're convenient for you. The more you work with them, you'll feel more comfortable. We will see much more with these in the next chapters. Monatomic ions are the ones that have only one element, and so polyatomic ions have more than one element. And the ones that you need to know are primarily listed in table 3.3. For polyatomic ions, the entire group of atoms together has a net charge, and so it's not just one atom, but the whole group of atoms. We'll talk more about that in chapter 4. The ones you will most want to know soonest are noted here on this slide. They were also in your Pogel activity, and they are nitrate, carbonate, sulfate, phosphate. Notice that they all have a similar kind of an ending there. Not that that helps you remember them. Whoops, back up. Not that that helps you necessarily know them, but the endings are not going to be the IDE endings that we saw for monatomic ions. Those tended to end in IDE. The chart shown here from the textbook, as mentioned today, hydronium is never going to show up in ionic compound formulas. Chromate, dichromate are ions that are seldom encountered in our course. I wouldn't put them on your list of priorities. Oxalate does not ever show up in a common way for us, and the rest of these is plenty. So take note of most of these, and primarily realize that you will be using these much more when we get to reactions in chapter 6 and some in chapter 5, both some in chapter 5 and 6. So if you wanted to take a preview of the problems at the ends of those chapters, you'll see where some of these become much more common in the examples. Okay, so let's name a couple compounds just to practice it. Think it through, make sure you get the right ideas. Whenever you're naming compounds, all you need to do is you name the cation first, and you name the anion second. And so it's nothing too tricky if you recognize what they are, and there's not any extra information provided unless it's a transition element. So here we name the first one and the second one. If you remember element names, this is lithium, and its component that's the anion. Remember, they're going to have endings change to IDE when they're anions, and so the iodide becomes the second ion here. All right, the next one will be with SR, which might not be familiar to you. Look it up in the front cover of your textbook if you need to, but it is simply strontium. It's a group 2 element, and the group 2 element combined with sulfur becomes a simple binary molecule. So strontium with sulfur as the anion, and if you think for a second, you'll realize what sulfur is as an anion. So you change the ending to, as usual, sulfide, and put the name together as simply as that. Sometimes we overcomplicate matters when we forget how they're supposed to be done. How does the name change then when you have Al2S3? Well, Al is, I bet you remember, aluminum. And aluminum has nothing further to name in its name. And the second ion is then the same name as we had up on the previous example, so this is simply sulfide. Notice that it has no reflection whatsoever in the name that directly specifies anything about the numbers. You know what the numbers in the formula should be based on the charges of the two ions. We'll talk about writing formulas from names after a few more slides. All right, example over on the left then. Let's do another one. First element again is from group 2, somewhere down towards the bottom of group 2. It is barium. Leads to bad jokes, as in what do you do with a dead chemist? And simply stating its name as that, nothing more. Uh-oh, my tool isn't working well again today. Sorry about that, gang. The second name is, of course, the Br is bromine, and then you'll change the ending as we've done on the other one, so it will become simply bromide. Nothing more to write. Doesn't tell you that there's two there, but you realize that the electrically neutral formula reflects the fact that barium has a +2 charge, bromine has a -1 charge, and there must be two of the bromine to make that work out. The first example, lithium is +1, iodide is -1, so one of each. Strontium was +2, sulfide is -2 because it's in group 6, and aluminum is +3 because it's in group 3A or 13. So in order to put a +3 cation with the -2 sulfide, you have to have 3 of the sulfide and 2 of the aluminum. In other words, the charge on one becomes the subscript on the other. We've done that a time or two. All right, last two. These include the fun things called polyatomic ions. And again, we only name the metal cation as it normally gets named, so it's still lithium, just as it was in the previous example. Just that my tool doesn't make it readable today. I'm sorry about that. And the lithium here has a charge, as it always does, of +1. There are 2 of them because sulfate is your other ion, and so sulfate is going to be listed just by its name. Nothing more to say. Sulfate. The last example is Ca, which is another group 2 element, so it's a +2 charge, which is our good old friend calcium. Think of healthy teeth and bones. And so we'll spell out its name. Again, the name of the cation is only the name of the metal here because there's nothing else tricky here. And calcium with NO3. Well, you're going to learn these with time. NO3 is a nice ion because it has some interesting properties that are handy to us later. And that one has apparently 2 of them with calcium, so its charge must be -1. And with the -1 ion is nitrate here. Okay, enough for that set of examples. Now, remembering how we put together formulas. Formulas of ionic compounds are designed so that the number of positive charges equals the number of negative charges, resulting in something that is an electrically neutral compound. And we did this not long ago with rules, but it wasn't Chem Activity 9. The numbers have changed now. That would be in your Poggle books in Activity 11. The idea is we're going to use parentheses as needed to surround an entire formula of a polyatomic ion when there's more than one. You've seen some examples of this, and normally this isn't too tricky, but we need to pay attention how the charges work. The charge in this example is -3 for phosphate, +2 for magnesium. So the charge on the magnesium provides the subscript for the phosphate. The charge on phosphate gives you the subscript for magnesium. It's pretty easy to think of it that way if you'd like. So let's do another example. If you have lithium from group 1A with a charge of +1 with sulfate, lithium is going to require 2 of them to make that come out even with 1 sulfate. So 2 +1 ions, 1 -2 gives you lithium sulfate. In this case, there's not more than 1 of sulfate, so you don't need parentheses. Let's try another example, complete with sound effects. If you put calcium from group 2 with its +2 charge, combine it with nitrate that has a -1 charge, so you've got one ion with +2. You'll need to have two nitrates to make it go together, and this time we'll write a parenthesis around the nitrate to represent and put the 2 after it to show that there's 2 of everything inside the parenthesis. Here's some examples that will be similar to things you've seen in your homework. If you think about what the likely formula is for the ionic compound suggested, in other words, what if you put the red element right down here, whoops, the red element with the red element on the right. And so you have to deduce what their charges are going to be. The red element on the left would be in group 2, so it should have a +2 charge. Back up, I apologize. Okay, so the red element being in group 2 on the left would have a +2 charge. The element on the right that's combining with it is a nonmetal in group 7, so it should have a -1 charge. And without specifying directly which elements these are, and you can look them up if you'd rather, you can deduce that there should have to be 2 of the anion, 2 of the nonmetal to go with the metal from the left side, and so the formula should be Mx2, 1 metal and 2 of the anion. Now, what about the blue elements? So let's look at the blue elements too. The blue element on the left should be a charge of +1, as anything is in group 1. And the blue element on the right is going to be in group 6A, so that should have a charge of -2. So which one do we need 2 of? We need 2 of the element on the left, and so there will be 2 of the metal this time, and 1 of the anion. So we put blue with blue. The formula should be M2X. If you wish to look them up on the periodic table, you can deduce exactly which elements they are. And so the formula for the red compound would be from the 1, 2, 3, 4, 5th element in group 2, namely 1, 2, 3, 4, 5, barium. And the anion on the right is in group 7, the third one down in the group 7 has to be bromine. So that would be barium bromide, to be identifying them directly. If you identify the blue element on the left is the 1, 2, 3, 4th one down in the group 1 elements, that would be potassium. And the blue element on the right is the second one down in group 6, and that would be sulfur. So there would be K2S, and we could name that as potassium sulfide. The other one would be barium bromide. All right, a couple more examples just for fun for pretty compounds. The mineral chalcanthite, not that we're going to remember its name, is a form of copper 2 sulfate. What would its formula be? So here's an example that requires you to remember what to do with Roman numerals. Copper 2 tells you the charge on copper, so it's going to be copper 2 ion. And sulfate, you have to recall or look it up, is going to be a -2 ion, and its formula is SO4. Well, I should have put the charge with it. How about that? And so sulfate with a -2, copper with a +2. What does the formula need to be? Apparently, we only need one of each. Simple as that. Copper 2 sulfate is going to be very simply written. Whoops, my tools are being picky today. Okay. Now, the next one is another example. Barium sulfate is something that's known as barium cocktail, used in visualization for X-ray procedures. The barium sulfate is very opaque to an X-ray. It's a very chalky substance if you've ever heard about anyone using it. And it coats the stomach and colon and shows up nicely on an X-ray. So what would the formula be? Well, you've got to remember where barium is. It's in the group 2 elements on the right in alkaline earth metal. And then we just talked about sulfate a minute ago. And so sulfate is a -2 ion. And so the formula becomes simply to put the 2 together, one of each, to come out with an electrically neutral compound. Okay, there's the formula for the compound. Sorry about the technical difficulties with the pen. I'm not quite sure what's up with that. All right, a couple comments about acids and bases, which we really did describe the other time in class, which doesn't require a lot further conversation, but I'll give you a few more pieces of information for the moment. Hydrogen ions and hydroxide ions are exactly those things which identify acids and bases. The hydrogen cation is literally a proton. If you remember that hydrogen, the element number 1, has 1 proton and 1 electron. And so if that 1 proton loses its 1 electron, then you have the hydrogen cation. And so the hydrogen cation really does equate to a proton. It does sound a little funny at first that a proton could be floating about in a compound that way, but that's definitely an accurate way to describe it. The hydroxide anion is characteristic for bases. It is a polyatomic ion, although polyatomic in this case is only 2 atoms. So any acid is something that provides hydrogen ions in solution in water, because that's the kind of things we're generally going to describe. And there, as you noted the other day, the hydrogen atom is shown at the front of any of these formulas typically. And so whenever you put them in water, for example with hydrogen chloride, HCl, the hydrogen ion is released into solution. A base will provide hydroxide ions when dissolved in water. The typical ones are going to be with group 1 and 2 elements, and they're the most common ones. They're cheap and ordinary. And so sodium hydroxide, potassium hydroxide, barium hydroxide are examples of those things. Pretty pictures result if you think about where sodium hydroxide comes from. The sodium ions are formed when you put sodium into water. It provides a lot of heat and smoke, and sodium dissolving into water results in, reacting with water gives you sodium and hydroxide and hydrogen gas, which is interesting and fun experiment because you can put a match to it. Okay, so let's do a couple more things of examples of things that are common ionic compounds and where they're used. Think about names and formulas and how they go together. Ammonium carbonate is something you might have heard of. Could be in smelling salts. It's going to have an ammonium ion that may or may not be as most familiar to you. That's NH4, 2 of them, because ammonium is a +1 cation and carbonate is a -2 anion. So it takes 2 ammonium to go with 1 carbonate. Calcium hydroxide. Well, I wonder what the formula of that should be. So think about it. Calcium being in group 2 and hydroxide is a -1 anion that's used in what's called hydrated lime. It's also related to the one below it in the list here. So it'll take 2 hydroxides to go with each calcium. All right, try another one. Calcium oxide, same thing, +2. But oxide is another ion that is just a simple monatomic ion. That one's going to be -2 ions, so it only takes 1 of each. Calcium oxide is simply CaO. Lithium carbonate. Lithium is in group 1. Get familiar with these the more you do. Carbonate, as we mentioned a minute ago, is -2, so it would take twice as many lithium to go with it. So lithium carbonate is Li2CO3. Magnesium hydroxide. Magnesium hydroxide is in milk of magnesium. Magnesium is another one of our group 2 simple cations, not hard to remember. Hydroxide, mentioned it already, is -1. So it'll take 2 hydroxides to go with each magnesium. MgOH2. Ironically, you already saw that one a long time ago in about chem activity 2, and most people were able to deduce its understand the number of atoms per formula without extra explanation. Magnesium sulfate's the one you used in lab this week with the +2 cation for magnesium. We did the formula of this the other day in class as well. Sulfate -2, 1 of each. Sulfate is what formula again? Must be SO4 with a -2 charge, so it's MgSO4. Potassium permanganate makes pretty solutions. Potassium's group 1 element. Whoops, in there I forgot to turn on the pen. But potassium is +1 and permanganate is -1. And so it only takes 1 of each to put that together. Potassium with nitrate, same idea, is +1 ion, and nitrate is a -1 ion. It's also described as saltpeter in some other historical reasons. 1 nitrate, 1 potassium gives you KNO3. Silver nitrate. Well, in this case, you have to know more about silver because it's not inherently obvious to you. But silver is only going to commonly occur as +1 ions, and nitrate is -1. And silver nitrate is something you'll use in lab. I believe you used it already to test for chloride ions, and so +1, -1, same NO3 ion, so you just put silver in front of it. There you have it. Okay, sodium bicarbonate, that's sodium. Oh, but what is bicarbonate? Bicarbonate is that funny way of naming hydrogen carbonate, but that gives you hydrogen carbonate, which is like carbonate that we saw a minute ago, but you put hydrogen in front of it. And so its charge for that ion becomes -1. So sodium hydrogen carbonate gives you NaHCO3. Sodium hypochlorite has been used and detected in bleach in lab recently. Hypochlorite is OCl, a -1 anion. +1, -1 only takes one of each. And then the last one, zinc oxide. We did that one in class recently as well. Zinc in this and most usual cases is going to be zinc +2, but that's kind of a hard one to say because it's not always specified in the name. Oxide, like the one we saw before, is -2. Same thing as up here. One of each, ZNO. Not bad. All right, enough said for the end of chapter 3.